Hello everyone, welcome back to the course Introduction to Multi-Agent Systems. In today's lecture, we'll talk about non-negative matrices and try to analyze under what scenarios do they become convergent. We already know that convergence depends on the spectral properties of the adjacent of any non-negative matrix, say. Let's say that matrix is A. Now, using the matrix A, we can treat this matrix A as the adjacency matrix and using that create a digraph that can be associated with that particular matrix. In this case, we can actually use properties of spectral graph theory to directly comment about the convergence of the matrix. Why is this useful? It's because spectral graph theory is a very visual tool. It allows us to directly look at the graphs and try to comment on the convergence or semi-convergence of the associated adjacency matrices. Okay, so let's get started with the lecture. Before we get started with the proofs, we'll spend a little bit of time in doing a quick recap of some of the notions that we've already discussed. This is because these notions will be useful when we are trying to prove things. So let's get started. So let us consider a non-negative matrix A, which is a square matrix. A which takes real entries which are greater than or equal to 0. So again, we assume that this A here is the adjacency matrix of some underlying graph. Hence, we write that we consider a square matrix A, which is associated with some digraph G. Now, what are the things that we already know? We know that A is semi-convergent if the limit of A raised to the power k when k goes to infinity approaches a finite value. Then we know that A is semi-convergent. Additionally, A is a convergent matrix when not only is it semi-convergent, meaning not only does the limit converge to a finite value, that finite value is equal to 0. Note that here it is a 0 matrix, so we write 0 n cross n. And otherwise, the matrix is divergent if it doesn't satisfy these two properties. Now, let's highlight one more thing here. When is a matrix convergent? What can we say about its spectral properties? Now, for a convergent matrix, this is again something that we have discussed in detail before, so I'll just write the result here. Convergence to hold, we must show that all the eigenvalues of A lie within the unit disk centered at the origin. So they lie strictly inside. So instead of within, let's just write inside and not on the boundary. At the origin. In other words, the spectral radius of A is strictly less than 1. So this is what we mean by convergence and semi-convergence. Interesting additional properties that we can associate with non-negative matrices. What are they? The first one is when we try to compute A times 1n for any matrix, what do we get? Let's see. And this goes to an1, an2 to an cross n. Let's multiply. What is 1n? 1n is nothing but the vector containing all 1. All entries as being equal to 1. So what does this product do? It gives us a vector such that every entry of the vector is nothing but the sum of each row, meaning the first term here, as you can see, get multiplied with this, and so on and so forth, meaning I can directly write this as summation of A1j, where j goes from 1 to n. Similarly, the second term is A2j, where again j varies in the same manner. And the last entry is a nj, where again j varies from 1 to n. Now, what is each of this term equal to? Remember that this is nothing but the degree of node I, the out degree of node I. Hence, I can simply write as A1n is equal to d out 1. Let's write this way, d out 1, the out degree of 1, the out degree of 2, up to the out degree of n, the nth node. All right, meaning the product A1n simply gives us the vector of all out degrees. So obviously, some more things which follow very directly is that if maximum of A1n corresponds to some node k, then it is equivalent to saying k has the maximum out degree of all the nodes. Similarly, the minimum of A1n now corresponds to some node j. Then j actually has the minimum out degree of all the nodes. So these are some things which follow quite directly. Let's quickly see this in an example. Let us look at the diagram which is shown here and compute what A1n would look for this diagram. So let's quickly write what the adjacency will look like. We observe that 1 has just one out degree, so one outgoing edge, which is to node 2. Hence, only that particular entry, A12, will be non-zero, and the rest are simply 0. Similarly, 2 has an outgoing edge to node 3. The other entries will simply be 0. Interestingly, 3 has two outgoing edges. One is to node number 4 and the other to node number 5. Again, the rest are 0. We see that node number 4 does not have any outgoing edges, hence all of the entries are 0. And similarly, this is what the fifth row will look. And now, if we calculate A1n, then what it gives us is nothing but the sum of all the rows. The first row sum is equal to 1. For the second row, again, it's 1. The third row is 2. The fourth row is 0. And the fifth one is again. Then, what do we observe here? If we just look at the network, we can directly see that 3 is the node which has highest out degree, which also follows from this. The maximum value of A1n is equal to 2, which corresponds to node number 3. So we can write the same thing in a more concise manner. Like, how do we indicate that this belongs to node number 3? So we can simply write this way. Sorry, this corresponds to node number 3, yeah. So we write E3 transpose A1n is equal to 2. What is E3 here? Please remember, E3 is nothing but this column vector times A1n. So what it does is, it simply picks out the third entry in the vector a1n. Similarly, I know that minimum of a1n is equal to 0, and the minimum occurs for node number 4, meaning is equal to 0. Let's continue discussing some more properties associated with non-negative matrices. Another one would be, for any non-negative matrix A, we can construct a matrix A bar, which is equal to A divided by maximum of A1n. What does maximum of A1n correspond to? Maximum of A1n corresponds to the maximum out degree of the digraph. When we do this operation, then the new matrix that we get, A bar here, it is either row stochastic generally or row substochastic. When we do this operation, then what we can say with certainty is all the entries of A bar lie in the range 0 to 1. Meaning so this is nothing but a normalization. In this regard, there are certain matrices of significance that we know have entries in 0 to 1. That is, the first one would be a row stochastic matrix, where all of the entries again lie between 0 to 1. And let's quickly write it. In this regard, we already know two kinds of matrices. First is row stochastic, where A1n is equal to 1. And again, and every Aij belongs to 0 to 1 for every ij. And similarly, if it is row substochastic, if there exists at least one row for which the row sum falls short and is not equal to 1 but is strictly less than 1. Meaning, so now if we want to consider a row substochastic matrix, then what we can say with certainty is there exists at least one row such that the row sum of that particular row is strictly less than 1. So we know that this operation does the row sum. This is how we would define a row substochastic matrix. Let's again quickly look at a small example. So this is something very straightforward, so we'll not spend too much of time, but just look at a rather simple example of it. Let's say we can construct any matrix maximum of A1n, it can be seen very easily, is the maximum A1n is equal to 6, 4, and 6 again. So this maximum is equal to 6. Meaning we can construct a new matrix now, A bar, which is given as this. Two by 3, 1 by 3. Right, and we can very easily see that all of the entries are here less than 1. Not only that, this matrix is also a row substochastic matrix. right? So that means if you are given a matrix A, we can always convert it into either one of these suitable forms to work with. Okay, now we'll get into the important part of the lecture where we start talking about some of the main results. So let's see the first result regarding the spectral bounds. Let's get started with that. So this is what the first result looks like. So in the interest of time, we have written it up already. So let's start. Again, we start by considering some non-negative matrix A, as shown here, and some associated digraph G, where A represents the adjacency matrix of the particular digraph. Then the following results always hold. What is the first result? It says that the spectral radius of A is upper bounded by the maximum out degree of the digraph and is lower bounded by the minimum out degree of the digraph. This is a very key result which directly tells us that if we take a matrix A, how can we directly comment on the bounds of the spectral radius or the bounds of the eigenvalues. The second property says that, now let us say the minimum out degree is strictly less than the maximum out degree. Then the following two properties are actually equivalent. What are the two properties? The first property says that, let us consider any node I whose row sum is equal to 1, whose row sum is equal to the maximum out degree, not 1, the maximum out degree. Then suppose there exists a directed walk in the digraph from that particular node I to another node J whose out degree is strictly less than the maximum out degree in the digraph. So here we have shown one small example. In order to make it a bit more meaningful, let me just draw some more edges here. Now, if we see this diagram, two nodes have been highlighted here. The first node here is a node which has the highest out degree or the maximum out degree. And this represents another node which simply does not have the maximum out degree. Then the condition says that in the digraph, there has to exist a walk from this node to the node which does not have the maximum out degree. That's it. If that condition holds, what we can always say is that the spectral radius of the adjacency matrix is strictly less than the maximum out degree in the digraph. So this is a very strong result which gives a very key upper bound on the spectral radius of the adjacency matrix. And this property is very useful in proving convergence results for distributed averaging based models. So let's look at the proof of this result. How does the proof go? Let's start. Just to quickly remind you, when we are interested, or let's continue with the proof. So the proof of the first part follows very directly from the results that we discussed in the previous lecture. So I'll not get into that. What is more of interest to us is the proof of part 2. Let's get started. Now, without the loss of any generality, we assume that the matrix, the non-negative matrix that is given to us, is actually row substochastic. So let us say if this does not hold. Suppose the matrix that is given to us is not row substochastic. What do we do? So if it doesn't hold, then we simply work with the modified matrix that we discussed before, which is sort of the normalized matrix. And we know that its entries always lie between 0 to 1. So without loss of any generality, we continue with this assumption. Note that here we want the matrix to be row substochastic and not row stochastic. So the proof that we will cover pertains only to row substochastic matrices. The proof for row stochastic matrices is not of importance here. It requires some more assumptions which we will not consider. Coming back to the proof, we assume that A is row substochastic, and since A is row substochastic, the following properties hold. What are the properties? The first is obviously A1n is less than or equal to 1. Why does this hold? Because we know that row substochasticity mandate there exists at least some j such that its row sum, which is given by EJ transpose A1n, is strictly less than 1. So this is an important equation for us. So let's highlight it because we'll use it later as well. Remember that it's about proving the condition that the spectral radius of the matrix should be less than the maximum multiply. For row substochastic matrices as well, in the most general case, the maximum of A1n is actually less than 1, less than equal to 1, right? Hence, we want to prove that spectral radius of A is actually strictly less than the maximum of degree, right? Which is 1. Hence, this is what we will try to prove, that rho of A is strictly less than 1. Now, in the beginning of the lecture, we started by discussing the properties of convergent and semi-convergent matrices. And we already know that if rho of A is less than 1, then A is a convergent matrix. A is convergent, right? What does it mean for A to be convergent again? In other words, it means limit as k tends to infinity, A raised to the power k should converge to the zero matrix. Meaning, our objective is to show eventually that the limit of, so our objective is to show that as k tends to infinity, all of the entries of A raised to the power k eventually go to 0, which is equivalent to saying that the spectral radius is less than 1. So let's write it. The objective for us is to show that, but what we will be doing is, rather than showing it for A raised to the power k, we will show that the row sums go to 0. Note that if the row sums go to 0 and all of the entries of the rows are actually positive, so it's like when we are adding up all of the, the entries are non-negative. So when we are adding all the non-negative numbers and the sum goes to 0, it is only possible when each of the entries also tend to 0. Hence, we will show that all the entries of A raised to the power k 1n tend to 0 as k tends to infinity. Again, equivalent to showing that the entries of a raised to the power k also go to 0. This happens because all of the entries are non-negative. Let's now get started with the proof. We start by analyzing what happens a raised to the power k1n under a specific condition. We start by showing what happens to a raised to the power k times 1n as k increases. When, or rather for a certain node j, which has a special property, which is okay. What does this property remind us of? So this property says some interesting things. That is, now we know that EJ transpose A1n is strictly less than 1 for some entries, right? It is given to us. It is the property of row substochasticity. Now, this implies that as we subsequently keep on taking the power, then there will exist some entries of a raised to the power k1n What is the condition? So we start by showing what happens to a raised to the power k1n as as the value of k increases for a certain node j which satisfies the property that EJ transpose a raised to the power k1n is strictly less than 1. What does this condition mean? It means that, and it's not, this is a very valid condition because we already know that because of row stochasticity, there will exist some value, some node h, which already satisfies this. Right? Strictly less than 1. Now, eventually, when we are taking all the higher powers, so we still haven't shown few things. So I'll just h1 and we'll call it sum h2. So it remains for the students to prove whether h1 is the same as h2 or not, which is actually not very difficult to show. Okay, so we know that there will always exist, so which implies that a raised to the power k1n is actually less than equal to 1. Now we know that owing to row substochasticity, we have a times 1n is less than equal to, again, 1n. So if we keep on now taking powers, so for example, I can show that now a squared 1n is, which is equal to a times n, which is less than a times 1n again, which is less than 1n. Meaning a squared 1n is less than equal to 1n. Similarly, I can keep on iterating it and we write that a raised to the power k1n is less than equal to 1n. So let's note down this property because we will use it later. So now we have a few conditions that we can use. So the first condition is that a1n is less than equal to 1. And the second is that a raised to the power k times 1n is also less than equal to 1. So now we start with the proof. So we start by showing what happens to the entries of a raised to the power k 1n equivalently a raised to the power k as k increases, or some node j. Ej transpose a raised to the power k1n is less than 1. Meaning, so we know that a to the power k1n is less than equal to 1. So we pick out the jth node for which it is strictly less than 1. Suppose kth power here is less than 1. What happens to the k plus 1th power? Will it continue to be less than 1? So that is very obvious. Now this implies that Ej transpose ak plus 1 times 1n. Again, we can write it as Ej transpose a times a raised to the power, we can write it as a times 1n, which is again less than equal to Ej transpose ak1n. So we can rewrite this as a raised to the power k times a1n. We already know from before that a1n is less than equal to 1. So I can directly substitute the condition here times 1n, which gives that. So we already know that for the jth node that we have picked, this is strictly less than 1, meaning this is what we get, which highlights a very important property. If the kth power of a raised to the power k, if the kth power of a is less than 1, this implies that, that the k plus 1th power times 1n is also strictly less than 1, which is something which follows very directly from what we already know. So what is again a raised to the power k? So meaning we are now simply talking about walks of length k and walks of length k plus 1. So meaning we are constructing walks and taking all of the path, the weight of each of the path, which is nothing but the product of all of the edge weights. And we say that for some kth walk, if the path lengths of all of the walks of length k starting from node j is less than 1, then for every other walk of length k plus 1 and obviously higher also remain less than 1. So there's a lot of equations in the proof, but those who are not interested can obviously skip the proof. Those who are interested, remember that this is not a very difficult proof to begin with. So we have shown that one part, we have shown one aspect of it already. Now we show a different aspect. So we now show what happens to the entries of a raised to the power k 1n, again equivalently a raised to the power k as k increases for a certain node I. This I has a certain property that it is connected to yet another node j. Let's write it with a walk to a node j which satisfies the condition Ej transpose a raised to the power k1n is strictly less than 1. Meaning, let's demonstrate what it means. The same has been shown graphically here. There's this node I which is connected with a direct edge to another node j, for which, sorry, there should be a transpose here. Ej transpose a raised to the power k1 and it's strictly less than 1. Now there's a little bit of algebra which takes us to the desired result, which is since Ej transpose a raised to the power k1n is strictly less than 1, we can just rewrite it as a to the power k1n, the corresponding jth entry is simply equal to Ej transpose a raised to the power k1n, which is equal to this. So again, we will use it a little later. So let me mark it here. So we already know from condition 2. Let me show you what was condition 2. So condition 2 said that a raised to the power k is less than equal to 1n. So basically, it showed that the entire vector is less than equal to 1n. Here, we are talking about some specific jth entry of that vector, which is equal to this, meaning using condition 2, we can write that a raised to the power k1n is less than and equal to 1n minus a raised to the power k 1n times e of j. So this is just rewriting the equations in a different way so that it is helpful for us in order to go ahead with the proof. So once we have this condition, the rest becomes very simple after that. So then let's consider what happens to those walks which start from the ith node and go up to. So then let's calculate so this can now be rearranged as E transpose. I transpose A times A raised to the power k into 1n. Now I can just substitute this condition here. Which will give me that it is less than or equal to EI transpose A times 1n minus So let's do some more algebra here. Okay, so some terms here are scalars. So note that this here is a scalar. So I will write it first. Times 1n into EI transpose A times EJ. What is this term? It can be easily shown that this term is nothing but AIJ. So now things are very straightforward. So we know that this entire term here, this is actually greater than 0, right? And this term here, EI transpose. Since the second term here is greater than 0, we know that this entire term now becomes strictly less than 1, which implies that directly follows from here that EI transpose A raised to the power k plus 1 times 1n is also strictly less than 1. Okay, so again, what did we see before? We saw that all of the path lengths here are strictly less than 1. All of the path lengths, again, in this case, become strictly less than 1. But while they are strictly less than 1, do they converge to 0? Can we prove that? The answer to that question is yes, they do converge to 0. And let's see how it happens. So we already have shown that if, let's say, EJ transpose A raised to the power k1n is less than 1, then walks of length 1 also satisfy the same properties. For some k here, which belongs to the set of natural numbers, further, EI transpose k plus 1 times 1n is also less than 1 for every I which has an edge 2j. Combining these conditions, the row substochasticity or in the light of the row substochasticity, we conclude, or it directly follows, there exists some k such that A raised to the power k times 1n is strictly less than 1 for some power. All that remains to show is that not only are they less than 1, but they also go to 0. Now, in order to show that, let us, for this kth instant, we define the maximum out degree as gamma such that gamma is equal to maximum over 1 to n for or of the summation a raised to the power k a raised to the power k and its ij entries. As shown here, this summation is strictly, this term gamma is strictly less than 1. Then what happens for, does this out degree remain less than 1? We know yes, but let's see, does it also further reduce? For that, then let's consider a different time instant k bar. A at an instant k bar which is strictly greater than k, meaning I can always write k bar as equal to sum C1 plus C1k times C2, where C1 is the quotient and C2 is the remainder when k bar is divided by k. A raised to the power k bar. Then we can calculate the powers of A at this k bar now and take its sum, and we can replace k bar with C1k plus C2 times 1n is equal to again AC1 times k into AC2 times 1n. Note that C2 belongs to the set of integers k minus 1. Hence, it is also an integer. Hence, a raised to the power C2 times 1n, we have already shown that this is less than equal to 1n. Hence, this implies a raised to the power k bar into 1n is less than equal to a C1k times 1n. Now, for the matrix a raised to the power k, we know that the maximum out degree is given by gamma. Hence, through some more manipulation, we can write that a raised to the power k bar times 1n is actually less than or equal to gamma times C1 into 1n. So this result follows again because of the fact that gamma here is the maximum out degree. So when we multiply it with 1n, so gamma is a scalar, so gamma times 1n gives us a vector, all of whose entries are equal to gamma. So obviously, we know that this matrix is going to be bounded by that. The matrix sum is going to be bounded. Okay. This now gives us a very interesting or important result, which directly leads us to the proof. Hence, as k tends to infinity, gamma C1 tends to 0, which implies that a raised to the power k bar tends to the 0 matrix. And we discussed at the beginning that this will imply that the spectral radius of A is actually less than 1, which brings us to the end, to the first part of the proof. That if we start with that specific form of the directed graph, then the spectral radius is now bounded above, strictly bounded by 1. Now, the other part of the proof, which is from 2 to 1, can actually be proven through a contradiction. Now, let me just mention it. Part 2B to A can be shown through a contradiction. The students are encouraged to try it out. And this brings us to the end of the proof here. So what did we learn in this theorem? It tells us that the above mentioned proof or result holds for a specific class of non-negative matrices. What are those classes? It's those digraphs for which the adjacency matrix can actually be converted to a row substochastic matrix such that there's a walk from every node of out degree 1 or the maximum out degree to a node of out degree less than 1 as shown below. So we see here the form of that the digraph is supposed to take, that we start with a node which has a maximum out degree, and again there is a walk to a node which does not have the maximum out degree. The result holds for all of these cases. Now there's another result which can be directly derived from this result, which is a simpler result which says that suppose we directly start with A being a non-negative matrix and also being row substochastic, then, and it is associated with some digraph G, then the network G, if it is strongly connected, in other words, if the A matrix is irreducible, then A will also be convergent. Now this result holds directly from the previous result, because in a strongly connected graph, we can, start from any node and reach any other node. Hence, there'll always be walks from the nodes with maximum out degree to those nodes which do not have the maximum out degree. Okay, so this brings us to the end of the lecture, and next lecture onwards, we will start talking about distributed protocol based on the adjacency matrix known as the averaging model. Thank you.